Looking at this surface that shows watts versus RPM and heart rate, we found that low cadence cycling helped increase the power quite a bit in hill climbing. But let's talk about flat terrain, 100 watts at 15 miles an hour or 210 watts at 20 miles per hour. I went out and rode on my trek on some flat road that had a very light breeze. I went out and back, collected the data, and it's plotted here showing heart rate vertically and RPM on the bottom. The lower curve I went back and forth at 15 miles an hour, and I would just shift up about 3 gears or 2 gears to the maximum, and even the highest point, most of the right point is on the lower curve is in the 39, shifted to the second largest cog in the back. And what happened is at 54, 55 RPM, I had a heart rate of 124, 123 and a half. When I fit a curve to the data, it came out at 125. It goes on up at 88 RPM. I had a heart rate of 136. This data fits 135. So a 10 or 12 beat increase going at the same speed, at the same power output, but riding at 88 RPM instead of 54 or 55 RPM. Now it's interesting to look at the difference between this curve and the 20 mile per hour curve above. There's about 27, 26 heartbeat difference for 110 watt difference. So there's about 4 watts per heartbeat. Now if you think that my heart rate goes up 10 or 12 watts when I choose to pedal at 88 RPM instead of 55 RPM, that's equivalent about, did I say beats or watts? My heart rate goes up 12 beats when I go from 55 to 88. That's equivalent to 48 watts. So I could be riding with the same heart rate of 136 at 148 watts instead of 100 watts if I chose to ride at 55 RPM. Now at the upper curve, I went from 150 beats per minute to 166 beats per minute, still at the same speed, 20 miles per hour, the same power output, 210 watts. That's an increase of 16 heartbeats, equivalent to about 64 watts that I'm not getting. Now, if I had really big gears, I could ride along at 57 or 60 RPM with my heart rate at 160 or 166. I'd be getting nice energy benefit from being at that low cadence, but I'm not getting it here. There are several reasons for this inefficiency. The most obvious is just the cost of spinning your legs with no load on them. Here's the curve. I'm riding on a exercise bike with no load on the wheel. As I increase my RPM, the heart rate goes up. It finally peaked out at 150 RPM at a heart rate of 153. But what's interesting here is the difference between 50 RPM and 90 RPM. And there's not much difference, maybe 5 heartbeats, maybe 6 in that range. Not a big difference, but when one heartbeat is worth 4 watts, that's possibly a 20 watt difference right there. So that's part of why it's less efficient to pedal faster. A second reason why high velocity can be inefficient, or high RPM can be inefficient, is the muscle fiber force velocity curve. On the vertical axis here we have the speed of a muscle fiber contraction, and on the bottom we have force. And if the force is very small, you can contract the muscle quite rapidly. The fiber will move very quickly. But as force increases, the fiber slows down until the point where there's so much force the fiber can hardly move it or can't budge it at all. Now, because this is force and velocity, you can multiply the two together so that for every blue point, I've multiplied the force and the velocity at that point to get a red point that gives me the power output. I've also scaled it down by about a factor of 10. So you can see it on the same graph. But you see the power goes up, it peaks at about 20 grams of force, and then it comes back down. Because of that peak, there's going to be an optimal speed and force combination at which to contract the muscle. Would be force on the pedal versus RPM in cycling. Here are curves that show you a lot about muscle fiber. I'm sorry, I can't remember where I got it from. I apologize to the authors that worked on this beautiful paper. But the top curve is fast twitch muscle from a mouse. The bottom curve is slow twitch muscle fiber from the soleus muscle of the mouse. And we're looking at the force that a muscle fiber will generate in Newton meters per gram of dry weight. They dry them out to make them more equivalent. And we're looking at the velocity in terms of length per second. So the length of the muscle fiber will contract in a second. So it'll contract. The fast twitch muscle with no load will contract 6 lengths in a second. The slow twitch muscle below will contract only 3 lengths in a second. And the lengths from sarcomere to sarcomere are about equivalent in these two types of muscles. So this is a pretty good equivalent comparison between what fast twitch will do and what slow twitch will do. Now, if you look at the top curve, the black circles, for about 0.5 Newton meters and over a velocity of about 2 lengths per second, you'll see that that's probably going to be pretty good for peaking the power, and 2 times 0.5 is going to be 1.0, a little over that really. And if you look at the next dot down the curve, it's going to be maybe 2.5 times 0.4 something, 0.4, it's going to be again around 1.0. So those two dots are pretty much near the peak of the curve, and the peak power is going to be 1. If we go to the slow twitch muscle and try to do the same thing, the 2 data points in the middle, we look at one of them, it's about at 0.3 in terms of force, and maybe 0.7 in terms of velocity, so 0.3 times 0.7 is 0.21 for power. And the next data point is going to occur at 1 times 0.21, so it's again about 0.21 for power. So the peak power of the slow twitch muscle is 0.21 versus 1 for the fast twitch muscle. So we get only about 1/5 of the power, somewhere between 1/5 and 1/4 of the power out of slow twitch muscle when compared to fast twitch muscle. Now, if you look at the open circles, that represents fatigued muscle. They stimulated each of these muscles, I think, about 30 times and then remeasured. And you see the drop-off in peak force of the fast twitch muscle drops from 1.5 down to about 0.65. In the slow twitch muscle, it drops from 0.8 down to 0.6. So not nearly the drop-off in slow twitch muscle. It has a lot of endurance. Even the speed of the muscle drops quite a bit. It goes from 6 or just under 6 to about 4.5, whereas in the slow twitch muscle, the drop-off is from 3 to 2.8 or 9. Very, very small drop-off. And so you also see the difference between the curve shapes. There's a big gap between the curves in the fast twitch and a very small gap in the slow twitch. So for endurance, of course, you want to use slow twitch muscle. But for power, for sprinting, you can get 4 to 5 times more power out of fast twitch muscle. We've seen that muscle fiber has the concave force velocity curve and therefore the power curve that we've demonstrated before, but what about the whole leg? And this curve shows the whole arm, at least. It was taken by Russian researchers back when Russia dominated in sports, and they had 100 athletes thrust their arm into the air as fast as they could, then with 1 kilogram, 2 kilogram, 3 kilogram, 6 and 8 kilogram dumbbells, and they measured the opening of their arm angle in radians per second. A radian's 57 degrees, so you could multiply that by 6 and you get, a number of degrees per second. The whole thing amounts to about 720 degrees at the fastest speed, 2 full circles per second. That's the rate at which their arm was opening up. Of course, it only opened up for a fraction of a circle. But if you think about that, that's sort of like a cadence of 120 RPM for the maximum velocity. And if you get down here to where we have peak, it's going to be much less than that, around 40 RPM or less. Anyway, the average data from the 100 athletes are these dark blue diamonds at the bottom. They go all the way up to 8 kilograms, but that's obliterated a little bit by the curve fit that goes over it. I tried to fit a curve to it, and as you can see at the top, I've got A over F0 equal to 0.18, which is well within the range of slow twitch muscle, but it's not concave enough. When I tried to make it very concave, I had trouble fitting some of the endpoints, at least the 8 kilogram endpoint, and so I just left it at this. And I only extended it because I wanted to see what happened to the power curve. You can see it originating at 12.6 on the right and coming up to peaking around 4. It looked like it was going to keep peaking as you got slower, but when I added this other data, it comes back down. So the peak power is below 4 and around 4 anyway, and that's less than 40 RPM in terms of the opening rate. The main point here is that the whole muscle works a lot like the fiber does. It has the same sort of velocity force curve. It's got the same sort of power curve. The purpose of this slide is to demonstrate what two muscle motor units might do given that one's twice as strong as the other. So one goes up to unit 1 of force, the other goes up to unit 2 of force. But they both have the same velocity because they're both slow twitch muscle. So as you get stronger, if you strengthen a muscle or if you have a larger muscle motor unit, it will produce more power, but the power will peak at exactly the same velocity. And so these peak at about 0.29. There's a turquoise curve for the top force velocity curve, and there's a dark blue curve for the lower force velocity curve, and it's about half as much power. Now what's interesting here is the brown curve, which shows the roll-off as you move away from the peak power, what percentage of power you lose. And it goes all the way to 1 on the left and all the way to 1 on the right, meaning 1 implying 100%. So if you pedaled or you moved the velocity, if the velocity of the muscle was 0.1, for example, over to the left on the bottom line, you'd actually lose about 30% of your power. If it was at 0.6, you'd also lose about 30% of your power. But if it was at 0.4, you'd be losing less than 5% of your power. Now I want you to take a good look at the shape of this curve, because it's going to look an awful lot like the curve that athletes generate when they ride at different cadences. In this study, relation between preferred and optimal cadences during 2 hours of cycling in triathletes, each triathlete was put on a cycloergometer with nose tubes and mouth tubes so that they could measure the oxygen uptake, and told to ride for 2 hours. Now, during the early part of the first hour, they had them ride at 50, 65, 80, 95, and 110 cadence while they measured their oxygen uptake. Then they allowed them to ride at their freely chosen cadence, which was typically 90-92 in that range, for the 2 hours. Towards the end of the second hour, they again measured them at 50, 65, 80, 95, and 110 RPM to see what their oxygen uptake was. They fit curves to the data as well. What they noticed was that their freely chosen cadence towards the end of the ride was down to 68 RPM. At the beginning of the ride, they had a little surplus energy. They could ride at a higher cadence, but they were getting tired, and they had to ride at the optimal level, which their body knows, and it moved to 68, which was very close to optimal. The difference between the curves in the first hour and the second hour is about 22 watts. It's about 3 milliliters per kilogram. They weighed 75 kilograms, so that's 225 milliliters of oxygen, which, since there's about 100 watts per 1,000 milliliters of oxygen, that's 22 watts. So if you look at the shape here, it's quite a bit like that power roll-off curve. You know, if you lined them up properly, you'd probably see that just the loss of power as you go in either direction away from optimum is enough to tell you that you're going to be breathing more oxygen. And so I actually tried to fit that. This curve shows the measured efficiency of the athletes, the triathletes, in the last study that we talked about. And if 0.03 would mean they've lost 3%, they need 3% more oxygen, they've lost 3% efficiency. 0.06 that they're breathing more, they've lost that much efficiency. The blue dots show the curve from that study that we just looked at. The red dots are my prediction of where that curve will be based on just the speed-force ratio and the peak performance of the power curve. And in the upper right curve, curve dot, I actually use 25% fast twitch muscle because it's at 110 cadence, and you are using fast twitch muscle. So I added that in to get that data point. Otherwise, the slow twitch would have been off the charts. And the correlation coefficient between these two sets is 0.987. So in other words, you can predict the efficiency either from too low cadence or too high a cadence of someone pedaling based on just the muscle force velocity curve and the power curve that results from it.